Okay. Hey everybody. So today we are going through chapters 1.2 and 1.3 in Hartshorne. Chapter 1.2 is very easy and very short, which is why we're doing two of them. 1.3 is probably going to be the most difficult lecture that we cover for a while. Heretofore, it will probably be one of the most dense lectures that you guys see in your lives, actually, because that chapter is hell. I spent, so just for context, 1.3 is on morphisms in the category of varieties, and it goes from pages 14 to 20, so 6 pages. I spent 3 weeks on those 6 pages. And so I'm going to attempt to condense that, but we may not condense that. And so um, it's something that we're gonna have to kind of take as we can get through. We're really getting closer and closer to the point at which we hit the point where I don't know everything. And as we hit that point, that means we're going to have to slow down. Um, so, of course, it's key with all of this, since we're doing this with research applications in mind, we have to both keep the mathematical rigor, not push ahead for the sake of pushing ahead, and then tie it back to application. And that's a lot. So, last time we ended really by talking about how dimension forces properties of affine varieties. So just recalling, the thing that makes affine varieties different from vector spaces is the fact that we don't really preserve this idea of zero. Um, and so basically we said that any two curves, polynomial functions of the same degree in the Zariski topology, had to be basically uniquely identifiable. Now we didn't put them into an equivalence class, but we did say that we could just call any polynomial of degree d the affine curve of degree d, because essentially they're homotopic. Um, and so where this kind of got us was up to this idea of dimension forcing this to be true as well. Um, and so we had this relationship between prime ideals, and then like irreducible varieties, and maximal ideals, and like uniquely factorizable varieties. Um, we talked about Noetherian topologies and Noetherian rings. So Noetherian topology means descending chain condition. Noetherian ring means every ideal is finitely generated. Um, and so the condition for Noetherian ring is really just like it comes out of Hilbert's basis theorem, which, in case like we use it a lot, so hopefully you guys are familiar with it. But if the underlying field that a polynomial ring draws coefficients from is a principal ideal domain, or even an integral domain, then every ideal is finitely generated in its polynomial ring. So pushing forward from that, we said that every algebraic set, not just varieties, but algebraic set can be expressed uniquely as a union of varieties, none of which contain each other. Um, and so then, if X is a topological space, we can kind of define its irreducible closed subsets by the longest chain of irreducible varieties that are self-containing, right? So if we factor X into its irreducible varieties, and we take the chain that you can get out of each variety, then that's the dimension. Now, an analog of this is that in a ring, the height of a prime ideal is such a chain, um, and it actually turns out that these two things correspond directly. And we're going to talk today at length about the fact that a variety and then the the a of y, where did I define it? Did I define a of y? It's gonna be funny if I didn't. It's affine coordinate ring. So, did I define affine coordinate ring? Okay. So A of y, just for context, is a quotient M. So if M is a maximal ideal of A of y, then we can directly correspond the affine coordinate ring. Wait, is it any prime ideal? Hold on. 1 second. I want to make sure that I do that right. No, it's A quotient, the ideal generated by y. That's what it is. Otherwise, it would be the residue field. So we get the ideal generated by y, which is just all of the polynomials which vanish on that algebraic set, and linear combinations of them. And then, yeah, A quotient, that is the affine coordinate ring. It's basically all of the functions that like are distinct from things that zero out on it. Thinking of it this way, since algebraic sets are closed, geometrically, then the things that don't vanish on the variety or on the algebraic set correspond to the functions which are distinct from the coset in A of y. So like, and I do want to draw this in because we're going to talk about this at length today. Like, if we have our little subset here that gets mapped over into our polynomials here, then all of the distinct stuff, which isn't in the yellow, like these are all points, and then these are going to be polynomials that don't vanish on the closed set. And so I'm going to call these open points. So we have this implicitly geometric identification of the dimension of an algebraic set and its affine coordinate ring. We're going to talk a lot more about that distinction today. Yeah, we talked about Kroll's Hopta-Deal shots. And so basically this kind of forces the thing about continuity in the affine line. And then we said that in AN, a dimension, a variety has dimension n minus 1 if it's a non-constant irreducible polynomial. Okay, so moving on, starting lecture 5. Which that feels crazy to say. We've done a lot. So this is going to be section, maybe I'll do this in here. Section 1.2, Hartshorne. And then the title for this section will be Projective Varieties. And so in a similar way to affine n space, we're going to define projective n space over an algebraically closed field K. And it's just going to be this Pn over K, or usually just Pn. Where Pn is the set of equivalence classes over K of n plus 1 tuples. So it's the set of all equivalence classes of A naught, A1, AN. And we'll call this equals the equivalence class of P, just for simplicity. Such that that P is similar to congruent to lambda P. For all lambda in K. Oh, and then also not all 0. And so this is not like a very clear thing. So let me write this in a more explicit way. That for algebraists, this will make more sense. So it's the affine n plus 1 space minus the literal 0 point. And then really this is going to quotient by all of the points which lie on the same line through the origin. So here we do have an idea of 0. This is kind of what differentiates affine space from projective space. Is that, you could have in affine space two parallel lines, right? And we would identify these as the same line because we could turn one into the other using a linear transformation, right? And so then we would maybe say that, well, if this started at true 0 the way we think of it, then this starts also like at maybe 0 prime under some linear transformation. Well, here we would say that these are in the same equivalence class in projective space because we have a well-defined 0 point. And so like this actually does preserve angles and stuff. Now it doesn't preserve them perfectly. We'll talk more about that. But yeah, and so this is going to be quotient the set of all G such that basically F, G are collinear. Right, and so at first this seems like it really makes sense. But you're going to realize rather quickly that Pn is talking about a set of points, and then the quotient of this set is talking about functions. So what are we really identifying? We're really identifying arbitrarily points on the unit circle. And this is really the most implicitly geometric construction that we could make for this, right? We are saying that if we have a line like this and a line like this through the unit circle, that those are just the same thing and they go to the same point back here, right? And so then the way that we distinguish between points is that really points have a different angle here. And so in this way, we actually do preserve angles. And so this kind of, and I'm going to jump a little bit ahead of Hartshorne, but when we're thinking about like ideals in projective space, or even like varieties in projective space, we're not anymore thinking about the ideal generated or the variety generated by f and g. It's actually going to be the ideal generated by functions which have the same ratio as the coordinates of f and the coordinates of g. So like, for example, if we had x proportional to xy, right? Well, this is going to be the same coordinates as 1 to y, right? But that would also be the same thing as x squared proportional to x squared y, which would be the same thing as xy proportional to xy squared, and so on. So projective space builds out this family of things which kind of get mapped to these points under equivalence relations. And so then an element of Pn is called a point. Any tuple that gets mapped to the same point is called a set of homogeneous coordinates for that point. Now, homogeneous does not mean the same thing that it does in differential equations. So especially for Dr. Scott, and especially for people who have taken DiffEq recently, homogeneous does not mean equal to 0. Homogeneous polynomials basically from now on mean all of the terms of the polynomial have the same degree, right? So you could have like xyz plus x squared y plus zy squared is a homogeneous polynomial. But you add in something of degree 1, it's no longer homogeneous. And so this is actually like a very important thing to understand because homogeneous polynomials have a geometric construction attached to them. Namely, we can define all of the polynomials in certain variables of degree whatever by the same kind of proportionality that I was talking about a few minutes ago. So when we like to think about like the affine line or the affine curve of degree d, now we're going to be thinking about all of the things which are proportional of degree d, right? Proportional and homogeneous. So we're adding some new notation for something that we've used before. Now when we're talking about projective space, S is going to be our polynomial ring. And the important distinction is that with S, we start at x naught, not x1. Key here is that in affine space we do, right? Now, we're going to just make a definition that Hartshorne makes. I don't think we use it. So a graded ring S with a decomposition a graded ring is a ring with a decomposition S is equal to the direct sum d greater than or equal to 0 of SD, where each SD is a Z module, and then SD product SE is equal to SD plus E. Or no, it's not equal to, it's contained in. And then an element of SD is a homogeneous element of degree, whatever. Now, I'm realizing that when I say Z module, this isn't something that I think we've talked about, maybe ever. So let me clarify. A Z module is a finite abelian group. You've seen them before. um, but a Z module has this underlying structure that, we can think of other things as like whatever modules. And so you can get some cool things that generalize theorems that we proved about finite abelian groups categorically to the category of A modules. And so like tensor modules are a good example of things that we're going to care about pretty soon because they help build us like a good cohomology theory. There's this one really funny meme that I found the other day that I'm gonna try and share real quick because it really does relate. This might be my favorite joke ever. Um, so it says you'll ask an algebraic geometer what a topological space is, and they'll go on a tangent about how really a topological space is just something you can put a sheaf on. And a sheaf is really just something that gives you a good cohomology. So really what you should be asking is what cohomology is and then not answer your question. um, it all comes down to cohomology. That is like the state of modern algebraic geometry, is like cohomology or bust. So um, kind of the goal of like where I want to take this, by the way, for research and just out of personal interest, is I want to get us into the theory of cohomology, for derived categories, because that is something that I have a lot of friends doing research in. And so then we can pull from their insights and like stuff. Something about standing on the shoulders of giants, I'm sure. But yeah, so Z modules, you've seen them before. A modules give nice cohomologies. That's why they're important. That's why I'm not saying finite abelian group. Um, so an ideal, and we will use this definition. So I guess we do end up using the first definition. And I guess really, hold on. There's an important line Hartshorne has. So I'm gonna add this as like a corollary of the definition. Any element of S can be written as a finite sum of homogeneous elements. And this is just something that like is a geometric way of thinking about the space. Like if we're thinking about projective Euclidean space, what we're saying is that you can take any two points here and you can homogeneously project onto the 90-degree angle here to construct a triangle, whereas you wouldn't necessarily be able to take the hypotenuse. So this gives you Euclidean constructions if you fix your curvature. So again, this is kind of tying it down to reality, right? Yeah, so an ideal A contained in S is a homogeneous ideal if A is equal to the direct sum D greater than or equal to 0 of A intersect SD. So again, we're taking S to always be a graded ring. And so because of that, we have this decomposition. And so we're really saying like this is A intersect the direct sum the SDs. Meaning everything that's in A is in some gradient of S. Gradient not in the calculus sense. We call each of the SDs gradients, basically. Yeah, so I'm going to just write some facts down because Hartshorne deals with these loosely. So an ideal is homogeneous if and only if it can be generated by homogeneous elements. This makes sense. Another fact, the sum product intersection and radical of a homogeneous ideal are homogeneous. And then I guess I'll just say fact again. To test whether a homogeneous ideal is prime, we can show that for any two elements, F comma G in A, FG in A applies oh, these aren't necessarily in A. Hold on. For any two elements, F and G, that F and G are in A implies F in A or G in A. So basically, the if the product of two elements is in something, then either one has to be in there or the other has to be in there. Yeah. So we can make any polynomial into a graded ring by taking each SD to be the set of all linear combinations of monomials of total weight D. And so this is like an important construction that I'm going to kind of write out. So turning S equals K over X naught to Xn into a graded ring. So the way we'll do this is let SD be the set of all linear combinations of monomials of total weight D in X naught through Xn. And actually, that's just the only thing we have to do. So now, if we have a polynomial in this graded ring, we cannot use it to define a function on projective space because of the non-uniqueness of the homogeneous coordinates. But if f is a homogeneous polynomial of degree d, then we can use it to define a function. So again, this isn't even like a continuous function necessarily, but just a function at all. And so really, like, we are only looking at functions which are homogeneous. And so maybe put this as a remark. We can only define f in S to be a function if f is a homogeneous polynomial of degree d. And the justification for this is that f of lambda a naught through lambda an is equal to lambda to the d f of a naught an, which is exactly kind of what we want out of this. We want to be able to like restrict things back to our equivalence class. And then this kind of induces like the polynomial being 0 depends on the equivalence class of a naught through an. So f gives us a function from Pn to the set 0, 1 by f of p is equal to 0 if and only if f of a naught through an is equal to 0. F of p equals 1 if and only if a naught through an is not 0. Right, so this really like characterizes how we're thinking about functions in general. Morning. I think that might be one of my books. Oh, okay. Yeah, so here, I guess the remark I want to make has more to do with the fact that the idea of continuous maps being like how we hold topology together, and like a morphism in the category of topologies we said was a continuous map. Continuity is not really what we're looking at anymore. Right? We're going to define a morphism that like is going to make sense for this, but we're going to do that in chapter 3. Or in 1.3, chapter 1.3. And that's where that's the lecture that I said kind of like is 6 pages and took me 3 weeks. Is because like really understand, there's probably stuff that I will like be like, oh shit, that makes sense now when I'm like saying it to you. So yeah, there's a lot of that going on here. But anyway, the remark that comes from this remark is that we can talk about zeros of a homogeneous polynomial. Z of f is the set of all p in Pn such that f of p is equal to 0 for all f. I guess really, if T is a set F1 through Fs. Sorry, I should have clarified that. Curl F and T. There we go. And then if A is a homogeneous ideal of S, the zero set of the ideal is equal to the zero set of T, where T is the set of all homogeneous elements in A. So basically, we can restrict ideals to their homogeneous elements. And that's what it means to look at the variety of an ideal, or the algebraic set of an ideal. Okay, is this tracking so far? Okay. Yeah, if you have any questions at this point, or if there's anything where you're like, hey, someone else might ask this question, but I think it makes sense to me, please ask, just so that it brings it to the attention of people watching. And then, okay, final remark number 17 here. Just for context, what we've gone through so far is a page. It's been this paragraph. When I say Hartshorne is like the least friendly book ever, you feel like you're making no progress, but it's actually quite a lot of progress. Since S is a Noetherian ring, any set of homogeneous elements T has a finite subset F1 through Fr with the zero set of T equal to the zero set of F1 through Fr. So, okay, now we've gotten through a paragraph of remarks. All of the things that we want to hold is basically what we're saying, and this all kind of fits together as a puzzle. So we'll have a definition that a subset Y of P n is an algebraic set if there exists a set T of homogeneous elements with elements of S with Y is equal to the zero set of T. And again, this forms a topology. So I'm going to say this is one closed under union, closed under finite intersection, and three, the empty set and Pn are algebraic sets. And once again, we can define the Zariski topology. So yeah. Okay. So is all of this good so far? We're clear with how, yeah. So the same idea with the notion of an irreducible subset and the dimension of a subset from chapter 1.1 still apply. So all of the stuff that we did at the end of the last lecture applies directly over. So the dimension of a topology, the dimension of the chain of prime ideals, deciding the chain of the A of y, the affine coordinate ring. And so then we get to our big definition. A projective variety is an irreducible algebraic set in Pn with the induced topology, and then an open subset of a projective variety is a quasi-projective. And then the dimension of either is its dimension as a topological space. So another definition was that let Y be any subset of Pn, then I of Y is equal to the set of F in S such that F is homogeneous and F of P equals 0 for every P in Y. So again, now we're no longer looking at all of the things that zero out. We can restrict this to specific functions that are homogeneous, right? And so we're looking at like the class of all homogeneous functions which zero out on a point in a variety. What is this equivalent to? If we were trying to make geometric constructions with polynomials, but we were doing it in projective space, and we were thinking about like a triangle, the easiest way to think about a triangle in projective space is by mapping things like so to their points on the unit circle. Behold, a triangle. Right, and of course the triangle that we would be talking about in affine space would be this triangle in blue. In projective space, this is what we're thinking about. But if we consider these to be roots, with Y, some subset, not of S, sorry, of Pn, right, really in P2. Let me clarify that, right? Then what we're looking at is the functions which vanish on this are the geometric constructions for the triangle in our normal R2, right? So then Z of Y gives polynomials which construct the triangle in R2. What? Whatever. It doesn't matter. That's close enough. So is this clear?
Yeah, the picture is great.
Huh?
I said yes, the picture is great.
Yeah. Or sorry, not Z of Y, I of Y. There we go. That's an important distinction. um, Now we define the homogeneous coordinate ring. So again, before we had the affine coordinate ring. Now we're going to define, so if Y is an algebraic set, the homogeneous coordinate ring of Y is, and this is a little annoying, they switched the notation from A, but so S of Y is equal to S quotient I of Y. So it works the same way. Okay. So our next objective is going to be to show that projective n-space has an open covering by affine n-spaces. So every projective variety has an open covering by affine varieties. Show that every projective variety has an open cover, or really admits an open cover of affine. And like, what's the easiest way to make sense of this? Well, I've been using the unit circle as an example, but really we have to fix the radius of the unit circle for it to mean anything. But for any radius that we fix, we can definitely find an affine variety which fits that circle, namely the unit circle, right? So like RE to the I theta gets the job done every time. Okay. So introducing notation. There's always more. So one, if f and s is a linear homogeneous polynomial, then the zero set of f is a hyperplane. And so in particular, the zero set of xi is what we're going to call hi. I is equal 0 to n. So basically, we're taking the zero sets in one coordinate at a time. Again, our idea with the unit circle or the unit sphere like works nicely for low dimension stuff. For high dimension stuff, it's hell. So we want to be able to isolate one dimension at a time. And again, because this is linear, we can actually do that. And then let UI be the open set, which is Pn minus hi. So again, this is pretty clearly like the definition of an open set. So that works. And then Pn is covered by such UIs. And then we're going to define a mapping. Is the fact that Pn is covered by UIs clear? Okay. Yeah. Basically, if you pick finitely many points, you can just pick two finitely many points on the same line through the origin, and then you can omit one from the other. And so then the union of the two is Pn. I think that actually also works if you pick distinct points as well. So never mind. You don't even need that. Pick any 2 points on the unit circle. Their UIs, respectively, will cover each other. We define a mapping, and this shows up later, so I don't think we're ever going to use phi again without it meaning this. More on that later, in case I'm wrong. But phi I from UI to the affine n space is a map where if P is A naught through AN in the open set UI, then phi I of P, nope, gets sent to Q, which is the set of affine coordinates A naught over AI dot 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 AN over AI with AI over AI omitted. And okay, thinking about AN and PN, right? Well, what is PN? PN has dimension n plus 1. AN has dimension n. So this is a really important morphism that we're talking about here, because what we're doing is we're removing a dimension to project this back into affine space. And then this is a homeomorphism, which is like the topological version of an isomorphism, right? And so this is going to be our big proposition of this chapter, which gets the job done for showing that we have an open cover of any projective variety with affine varieties. So phi I is a homeomorphism to the affine n space with the Zariski topology. Okay, what is a homeomorphism? Well, a homeomorphism is a bijective continuous map. And it's a bijective continuous map that preserves open sets. So open sets, UI, are open in the Zariski topology on the affine n space, and vice versa. So we have inverse images of open sets are open. We also have that images of open sets are open, and it's bijective. All right, so inverse images of open sets are open. Images of open sets are open. Phi I is a bijection. So this is clearly bijective, just kind of by construction, right? We're sending open sets to open sets. We have to have as many of them in both ways. Everything in the codomain gets hit. Everything in if two open sets in the affine n space are the same, they have to have the same thing in the projective space, specifically the same UI open set. And then to show that this is inverse images of open sets are open, we can actually show that inverse images of closed sets are closed. And this isn't hard to do because that maps all of the points which are closed in AN back to the closed points AI, where HI, right? We're mapping these from their points in affine space. So inverse images of closed sets are closed. And then same thing, images of closed sets are closed. Well, we map HI to finitely many points, or really a zero set. And so, yeah, I don't even think we need to prove this. Basically, if whoever's watching this feels like you don't get this, maybe it's a good idea to prove this on your own. And I'm going to say proof sketch. So 3 is easy. And then 1 and 2 show that phi and phi inverse send closed sets. Closed sets. That's also pretty easy. It's literally you just grind out the notation. And then corollary of this is that if y is a projective, really, really quasi-projective, variety, then y is covered by y intersect the ui, which are homeomorphic. And actually, this isn't really, this is respectively. So this holds for both, is really what I'm saying. Which are homeo to affine respectively quasi-affine varieties. Okay, so what are we saying? We're saying that y is covered by the open sets, which we showed above, and then we showed that phi I is homeomorphic to affine varieties, and so projective and quasi-projective varieties have a topological covering by affine varieties. So in the exercises for this section, because we're now at the end of the section, the exercises for this section basically go through all the stuff that we spent so long going through in chapter 1, which basically, so the homogeneous Null-Stellensatz says the same thing as the affine Null-Stellensatz. Then we have all of the stuff about radical ideals that we talked about. We have the reverse inclusion lemma for both varieties and ideals of varieties. We have the lemma about the ideal of the union of projective varieties is the intersection of the ideals. We have the definition of radical ideals for projective varieties. And so basically, like, all of this structure from affine varieties carries over. And there's a few ways to prove it. You can prove it the way that it makes sense to prove it constructively, or you can prove it just by transitive property of homeomorphism, right? That structure carries over. Yeah. And then, so that's, I would recommend if you're following along in Hartshorne, 2.1 through 2.5 are good problems. And then, yeah, we can, yeah, there's some good problems in here. I think I'll send them out to the email chain. Yeah, there's a lot of good problems in here. So I want us to take a 5-minute break and get into one meet back here at like 9:10. Right. I'm back whenever you are. Okay. So, just gonna show like a brief picture of how annotated this section of my book is. Hold on, wait. I have to unblur my camera. So, So Hartshorne is a graduate textbook, and more specifically, it's a Springer graduate textbook. There's this meme I like that's like, oh, like in the wild, animals have bright colors to hide the fact that they're or to say that they're poisonous. Springer books are like that. Um, he starts doing this thing where he introduces things that he thinks you should know as notation, as something, because he forgets the fact that it's the introductory textbook to this field. So it's been a very painful process of like scribbling in the margins to say, oh, well, this is what the pullback of a diagram is, or like this is, something or other. So there's going to be a lot more pausing. We're going to even move slower through this than we have so far. Although we're making good time. We're at page 14. That's a lot. So, okay. So far, we have defined affine and projective varieties, but we have not discussed what mappings are allowed between them. We have not even said when two varieties are isomorphic. In this section, we will discuss the regular functions on a variety and then define a morphism of varieties. Then we will have a good category in which to work. And so, yeah. Yeah, we're going to think about quasi-affine and then quasi-projective varieties. And then that's just going to be how we want to do this. So convention, let Y in affine space. Oh, and I guess maybe let me add a section. Now that we're in 1.3, this is the section on morphisms. There we go. So conventions, Y and AN, the quasi-affine. So then definition, F from Y into its residue field is regular at P and Y if there exists an open neighborhood, which is like an open set. An open neighborhood U with P in U contained in the quasi-affine variety polynomials G and H in K over X1 to Xn such that H is nowhere 0 on U, and F is equal to G over H on U. And so then as an extension of this definition, F is regular on Y if it is regular for every P in Y. Now, the thing that's important that I'm not saying here is that it doesn't have to be the same two functions, G and H, at every other point in Y. Right? So we can find different open subsets where we have two functions which agree that make F regular in that open neighborhood. And so in a way, this is a very intuitive concept. In a way, this is a very unintuitive concept. So lemma A regular function is continuous when k is identified with the affine line on the Zariski topology. And we proved this last time. Now the analog of this definition, and it's so close that I can actually copy paste almost the entire definition for quasi-projective. So for quasi-projective, the only place where we change this definition is that the polynomials g and h have to be of the same degree. Homogeneous polynomials of the same degree. And then, yeah, this works. So any questions about regular functions? Okay, yeah, so we're going to use these a lot. So make sure, especially for the people watching the recording, think about this a ton. Because this is just so dense. Like everything that we're doing here, you could spend an entire class in a traditional like undergrad way on each definition, you know? And that is by and large like the JMU speed. And not that there's anything wrong with that, but we're on a more cramped schedule. Ideally, one would go that slowly. But yeah, so as a remark, as in the quasi-affine case, a regular function is necessarily continuous. An important consequence of this fact is that if f and g are regular functions on a variety x, and if f is equal to g on some non-empty open subset u in x, then f is equal to g everywhere. Indeed, the set of points where f minus g is 0 is closed and dense, and hence equal to x. And so this is kind of like, he has this as a remark. I'm going to call this the gluing theorem. And so, yeah, gluing theorem. And there's a topological version of this as well that's kind of a subset of this property. If f and g are regular on a variety, and any type of variety x, and if f is equal to g on any non-empty u, which is open in x, then f is equal to g everywhere. And this kind of falls out of the definition. But it's really cool. If two functions agree on an open subset of a variety, then basically they agree everywhere. And that's cool. Okay, now for the category of varieties. Yeah. This is going to be dense. Okay. So again, let K be a fixed algebraically closed field. A variety over K is any affine quasi affine projective or quasi-projective variety as we've defined. If X and Y are two varieties, a morphism, or an arrow phi from X to Y, is 1, a continuous map where such that for every open set, they use V open in Y, and for every regular function f from V to its residue field, the function f composed with phi from phi inverse of V to K is regular. So a morphism is a mapping between varieties such that the composition of any regular function with that mapping is regular, right? I think a picture here is worth 1,000 words. So if we have a variety X and we have a variety Y, and we have the residue field K, which is fixed, then we have this subset V in Y such that for every F from V into K, which is regular, that the function phi inverse of V, which is in X, to K is regular. And so then this is phi inverse. This is phi. And then this is F circ phi. And then the idea is that really this commutes. So just mapping the path through here, right? We start in phi inverse of V. Then we go into V. But then we compose with F. And we end up at F of phi. And then this thing is regular. In that case, phi is our morphism. So this is the morphism between varieties. And this diagram is universal. So, this is like not the world's easiest definition. I'm just gonna let this sit for a second. Arseni, how do you feel about this with this definition? Like, do you feel like this is perfectly reasonable?
I'd say the diagram makes sense.
Okay. Yeah, so this diagram is universal, meaning that if you ever have a commutative diagram that looks like this, where f circ phi is regular, then your phi has to be a morphism between varieties. So it's the universal property of morphisms of varieties. And so clearly the composition of two morphisms is a morphism. That's not clear at all. But basically this is a category. This is a category. In particular, we have the notion of an isomorphism, where an isomorphism of two varieties is a morphism which admits an inverse morphism, which composes together to be the identity map. An isomorphism is necessarily bijective and bicontinuous, but a bijective bicontinuous morphism need not be an isomorphism. And this comes from exercise 3.2, which basically says, okay, so let phi actually maybe it's let's do exercise 3.2 before we go any further. Let's do exercise 3.2. Yeah. Because then we're about to get into these things called local rings, and ring of regular functions, and that's very difficult. Okay, so exercise 3.2. So a morphism which is bijective and bicontinuous need not be an isomorphism. And so for part A, it says let phi from the affine line to the affine plane be defined by t gets mapped. I guess let me do this underneath. T gets mapped to t squared comma t cubed. And then show that phi is bijective and bicontinuous. From the affine line to y squared is equal to x cubed. But then phi is not an isomorphism. And then by counterexample, of course, our claim is proven. Similarly, we could also define the Frobenius morphism, which we'll do next. but I want to hit this first. So again, an isomorphism, let's see what an isomorphism is a morphism which admits an inverse morphism on the left and the right. And so basically what we're going to want to do is we're going to want to find some inverse morphism for the left, which is not a morphism for the right. And since inverses are unique, basically if we can find a right inverse and a left inverse which are distinct, then this is not an isomorphism. So we want to take something from all the sets of t squared and t cubed back, basically. So again, let's do this by diagram. So if we have A1, we have A2, we're letting phi be the morphism that phi of t is equal to t squared t cubed. And then we want to send this back to the residue field K. So we want to find some F into our residue field. And then they give us this for free, that it's going to be 0 is equal to x cubed minus y squared. And what we want to do, this is phi inverse of t squared comma t cubed. We want to get this thing going back into K, which is phi inverse circ F. Wait, does that make sense? We have no, we want to find, we have phi inverse. No, we have phi circ. Wait. F circ phi. Which commutes here. So we can pick any t. We get it sent to t squared t cubed. And then we send that through F. And this is really saying that t squared cubed minus t cubed squared is equal to 0 by our parameterization. And that seems like that would make sense. But then we want to find this phi inverse where phi of t composed on the left with psi, which will be coming from t squared comma t3, is equal to the identity of t on A1. And then we also want a theta t squared comma t cubed circ 5t equal to the identity on the affine plane t squared t cubed with theta not the same as psi. So categorically speaking, does this make sense?
Hardly.
Okay. Yeah. Like this is where we really start doing algebraic geometry. This is where the rubber hits the road. Like it's nice to write down definitions and stuff. This is yeah, this is kind of like launching the first plane from Kill Devil Hills kind of thing. So this is, by the way, if psi and theta were the same map, then this would be an isomorphism. But the key that we're doing here is that the affine line and the affine plane can't be isomorphic, right? Now it would be like saying that the integers are isomorphic to Q, which we know is not true. They have the same cardinality, but like they're not the same thing. This is us saying that because one projects into another, theta and psi can't be the same thing, right? So we don't even have to find anything except for like the inverse. Like technically we should compute the inverse from the left and from the right. But the fact that they take in one takes in two things and one takes in one thing should tell us everything we need to know, right? Like this is an issue of dimensionality. I'm just doing the setup formally so that if we had two things that were varieties that were of the same dimension, we could show that like potentially they're not isomorphic. This is something I really have beef with is a lot of people who don't do abstract algebra but maybe work in physics or something will use the word isomorphic kind of to say things are structurally equivalent. My dad does this and it pisses me off like nothing else. I love my dad. I love him so much. When he says the word isomorphic about things which you can't even define as a category, I want to throw myself out the nearest high window. Um, because this is like the pain it takes to set up an isomorphism for real. And like, so anyway, um, yeah. um, and so I'm just going to say this comes out of the dimension of A1 not equal to the dimension of A2. Like we can find the inverses, which are maybe just going to be taking, I guess, the specific f doesn't really matter here. Maybe taking, or I guess solving this in t to get that f of whatever is t, right? So we can just project somehow down to t, but maybe we take, let's see. So we start. Psi has to send something back to t. So psi of t squared comma t cubed is equal to t, right? And then theta of t is equal to t squared comma t cubed, right? And that accomplishes this, right? And these are very clearly not the same thing. So So it is a morphism, right? Like we have the relationship, we can establish the relationship. Um, but not an isomorphism. Okay, let's do part B because they introduce, so this is the thing that Hartshorne does that is really painful. He introduces definitions that you need in the exercises. And so a lot of what the lectures are going to become is going to be us working through exercises together. And in this way, it'll behoove all of you to get a copy so that you can look at it and flip through it and annotate it. Now, we're going to kind of jump back and forth between Hartshorne and Vakil, basically because Hartshorne sucks. But Vakil does stuff that we don't need. And so we need the stuff in Hartshorne, but Vakil writes better. And so it puts us in this weird spot. So I've kind of put it together, but you should really get both books. And it helps to take a look at the problems ahead of time. So for 3.2 point B, we're going to define the Frobenius morphism. And so we're going to say, well, we're let K have characteristic P greater than 0. It's worth noting this gives us this thing called a mixed characteristic. The polynomial ring over K is an infinite field, or is an infinite ring, right? Whereas our residue field is a finite field. So this is called a mixed characteristic geometry. And so this is actually the big kind of thing right now. It's like the very popular research topic is mixed characteristic algebraic geometry. Define 5a from a1 to a1 by 5t is equal to t to the p. This is called the Frobenius morphism. Now this generalizes, of course, to higher dimensions where 5an goes to 5an. By phi of your tuple goes to each entry of the tuple being raised to the pth power. Well, let's just work through an example here. Maybe let characteristic of k be equal to 5, right? So then k is equal to z5 because there's exactly one group, which is of dimension 5, or one field of dimension 5. And so then we can take like phi of 3 is equal to 3 to the 5th mod 5, which is congruent to, let me see, maybe we should have picked a smaller p. 3 to the 5th mod 5 is 3. And so this is bijective and bicontinuous, but not necessarily an isomorphism because picking 3 was kind of just a lucky thing. If we had picked 4 to the 5th, 4 to the 5th mod 5. Nope, that's, hold on. I know there's got to be something, which is not. Hold on. Hmm. Well, but then how is this not an isomorphism? Oh, I know how it's not an isomorphism. Wait. I just need to check something. Um. Ah, okay. I have the answer. So if P is prime, then yes, this is an isomorphism. So we need to pick a P that's not prime for this to work. Because then you get a torsion group. So, okay. So let's let this be mod 6. And so then phi of 4 is 4 to the 6 mod 6. 4 to the 6 mod 6 is, there's no way. 2 to the 6 mod 6. Okay, that gives us something that is not itself. So 2 to the 6 mod 6 is 4. There we go. All right, it only took 8 minutes to figure this out. Right, and so this is kind of our example that it's not an isomorphism is because you get different things. It's not an identity map, and it's not even an automorphism because, and here is the aha moment that came from that, 4 to the 6 and 2 to the 6 go to the same thing, meaning that there must be, by the pigeonhole principle, something in elements 0 through 6 which definitely do not go back. Right? And so phi cannot be an isomorphism basically by pigeonhole principle. Okay, so I think that it's a really bad idea to start some new definitions. I think this is a good spot to end. So we have gotten right up to and really like just barely started the content from hell, we'll call it affectionately. And so next lecture tomorrow morning, we will deal with this, and it will basically just be a lot of examples, and it'll be a lot of things to kind of wrap heads around. But it'll be a lot of examples, and hopefully that'll help. So, recording people, thank you for watching this whole thing. Today we've covered projective spaces and an intro to the category of varieties, what morphisms look like, and the fact that bicontinuous bijective morphisms are still not isomorphisms. And then it's dependent on basically the dimension of the variety. So, okay, cool. I feel like that's good. Arseny, do you have any anything you want to add to this?
No, I don't have any notes, no.
Okay, cool. I'll stop the recording. All right, have a good day.